And next we'll have Kristina Collins, KD8OXT from Case Western, talking about personal space weather station Grape hardware version 1 and pilot experiments. Take it away, Kristina.
All right, thank you very much, Nathaniel. I hope everyone can hear me all right. It's lovely to see so many familiar faces and names in the chat. And I'm going to take us from Tangerine Land back to Grape Land. This is the low-cost personal space weather station that Nathaniel mentioned in the overview earlier. We call it the Grape because that makes it a good companion to the Tangerine and because it does its best work in bunches. And this is the first of 2 talks this morning. The partner one will be John Gibbons, N8OBJ, who's going to give a talk focusing on the hardware in a little bit. I'd also like to mention for context the co-design session tomorrow, which will rely on some of the same concepts that we're exploring in this section. I always like to start with, for the folks who aren't looking at Doppler things all the time, the cartoon version of how Doppler shift works. There's a couple of brief summaries linked here on the page. What we do is we have a precision beacon, WWV or another time standard station, and the reflection off of the control point or point of reflection in the ionosphere, which moves up and down with changes that are daily or seasonal or the result of some geophysical event, leads to Doppler shift in the received frequency at a station. So you can take your ham receiver and a precision frequency standard and look for that change in Doppler shift, and it gives you something of a proxy measurement for what's happening up here. So for us in Cleveland, that would be a point somewhere outside Des Moines, Iowa. Where that point is moves around a little bit, but in the abstraction, that's basically what we're looking at. So if you take this measurement over the course of a day, you'll see a plot that looks something like this. You can also see it in John's little image in the chat. And the black line here is the change in frequency over the course of 1 UTC day. Red is the change in power that is received. This bump in the middle is correlated with local sunrise. We'll see that again in a couple of slides. So over the course of the past year, we've been running pilot experiments using the Grape 1.0 hardware, which is what I had on that first slide. It's a little board that's about the size of a quarter. And we have individuals who are running long-term experiments with this. We've got David 88Y, John N8OBJ, have been using this to do data collection on multiple different frequencies, as has Bill AB4EJ. We have college clubs deploying these, W6BHZ at Cal Poly, W3USR at University of Scranton, and K2MFF at NJIT. And then our control station, Maxwell W3LLA, keeps tabs on things for us in Fort Collins. And is our control station. So he has very flat graphs for comparing hours to. And then in addition to the things we've been doing with this, we've also been kind of getting a glimpse of what having a fully fledged Grape network might look like in the future by having pilot experiments where we have ham radio operators use their existing HF rigs to take similar data using the frequency analysis modes of FLDigi. So the first of these was the WWV Centennial Frequency Measurement in October 2019. And then we followed those up earlier this year with the Eclipse Festivals, where we applied the same data collection procedure in order to look at the June and December eclipses. And those are under analysis. I've got some senior projects working on them who'll have a poster tomorrow, so you should come by. The next thing that we're working on right now is we've been deploying stations along a great circle path across the continental United States that intersects with WWV so that we can do ray traces in 2D and compare them. And if anyone here is in Des Moines, Iowa, or knows anyone who is, that's the next spot that we'd like to set up a station. So send me a message after the talk if you can help me recruit someone there. So as I was putting this together, I was thinking about how to compare the different data sets, and I identified 3 different domains of things where we're looking at varying our experiments. Here's our little appropriately radar plot for comparing them. I'm going to have this in the margins and in the slides as I'm comparing one experiment to another. So ideally, we'd, for the most part, like to branch out in all of these directions. But as we're doing experiments that are focused on one thing or another, we may focus on one direction at a time. And there are some trade-offs to these, not necessarily technical, but logistical, that need to be noted as we do more pilot experiments and develop a bigger network in the future. So the 3 categories that I chose. Scale is anything that affects the dimensionality of your data, the area that your network covers, the amount of time that you're accounting for, how many stations you have. Focus is what is scientifically interesting. So geophysical events of interest, are you just looking at the day-night terminator? Are you looking at an eclipse? Are you looking at an event of some kind? And then fidelity, how much you can trust your data. So not only the obvious elements of how good is your radio's oscillator, how good is your sampling, how much data are you taking in, but also when you're looking at multiple stations, what's the density or the sparsity of those stations? And kind of arbitrarily, I've been rating these, you know, on sort of a 1 to 10 scale in making these little plots. So there's plenty of other ways to look at this. This is just the way that I happen to choose in order to compare these experiments. I may continue to use the system in the future, may change it, don't know yet. But for the moment, let's consider kind of our basis case is the thing on the previous slide where I have one station. So it's at a single point, and it's 1 on all of these different scales. And we're measuring 1 UTC's days worth of data, 1 point in space, nothing particularly interesting going on today, single frequency. And let's say for the moment that we have a good crystal oscillator that's at a steady temperature, but that's all we have. So GPSDO would bump things out a little bit in this direction, perhaps. So to talk about Grape 1.0 versus Grape 2.0, because we're getting ready to make the jump from our initial prototype to something that fits the different figures of merit that we assigned ourselves at the beginning of the project. Grape 1.0 does a single channel worth of data. Grape 2.0 will do 4 for all of your WWV and CHU monitoring needs. And Grape 1.0 uses in the software, again, the frequency analysis mode from FLDigi or similar frequency estimation algorithms. So when you have Grape 1.0, measuring a day's worth of data, you get out of it a plot like the one that I showed previously, where that's a derived data product. You're not seeing anything from the sideband, and so you can't see frequencies split off. Grape 2.0 will be looking at that sideband as well. So we'll have an improvement in the number of frequencies we're observing and improvement in the fidelity of that data. And then everything else here is a function of how we structure the experiments around it. So some things that we've been doing, this is an example. We've got David 88Y recording data. Each of these frames is 1 day. It's a bit of an eye chart, but you can see the dates go by here. And the trick to these plots, and unfortunately I couldn't get graphing for it to work, is if you look at the peak that is associated with the dawn, you can pick out the solstice and the equinox go by as the peak slides back and forth over the course of the year. So you can see some seasonal variation there just from animating plots like this. And we have some data sets going back for about as much as a year from David and John's stations. And that's starting to turn into something interesting. So I'm really looking forward to seeing what we get once we can get a better view of the sidebands as well. It's also worth noting that, as we all know, different frequencies have different propagation characteristics. This is a simulated example with the YouTube link for a little higher resolution of WWV on the left, David's station here on the right. This is the geographic midpoint for all of them. And then this is for, let's see, 2.55, 10 megahertz. from WWV to Cleveland. So when a line appears, a pink or purple line, you can judge that that's where there's going to be a propagation path. You'll see that those change over the course of the day. So by having measurements of the same, from the same point of different frequencies, you can also get a more complete picture. And by picking the frequencies, associated with time standard stations, you are comparing the same geographical path along the ground. So as we're going, into creating more experiments, and I want to, I see some familiar names in the chat from people who participated in the June and December eclipse festivals this past year. We're trying to improve on all of these different parameters. So the June festival, for the experiment across China, we had, I think, 50 stations and recorded, at least initially, that derived data product of the frequency estimation output. And for the December eclipse festival, 2 improvements were made based on the data that I got back in June. One was that we started having everybody record audio data, and the other was that the number of stations grew because many of the people from June came back and participated a second time, and I was able to refine the recruitment approach. So as time goes on, we pick up lessons from experiments, but there are some trade-offs in this. Oh, and I don't know if I mentioned, but December was also a longer experiment because we wanted to get more control data. There is something of a trade-off as you do these larger experiments. If it's just your station, it's quite easy to say, I will take this and I will leave it here for a year. It's a little harder to ask many people to do it. So one reason to ask people to use dedicated hardware platforms like the Grape instead of their own radios is that you're not taking up somebody's operating time when you ask them to run the experiment. Another thing that I think is worth noting as we do these kind of large experiments is that you can say within a large experiment, okay, let's examine a subset as though it were its own data set. And then you can also take data from a set of stations and you can connect things over time. So it's worth considering where things fit into one another in that way as well. A point that I want to make about density of stations. This is something where I thought about putting it in a different way than these other figures of merit in the little plot here, because it is, a function of the space and the number of stations. But for an experiment that covers a larger area and has the same number of stations, of course, the density inherently drops and you have to compensate. What we see in these 2 plots on the right here, this plot on the left where you can see all of these squiggly lines that are relatively well aligned is from the original Festival of Frequency Measurement, where we had 45 stations all in the continental United States. And on the right, I have the same experimental procedure for the June Eclipse Festival. The line you want to look at is the blue one. All of the stations are just ordered by longitude, and you can see the sunrise and sunset are marked on the plots. But because those stations are further apart, it's much harder to look at them and, inherently see the relation between the data and establish groups. The advantage of having clusters of stations, and what I like to say is that the grapes do their best work in bunches, is that when you have, for instance, 4 stations that are all in the same area as one another, you can very easily pick out from comparing their data whether something that you're seeing in your plot is geophysical in nature or if it's that your dishwasher turned on in the next room. So as we make our experiments cover larger areas, we have to be cognizant of improving that density number, either by having clusters of stations that are in certain areas or just bringing up the number of participants in general. So our next steps, as we go from Grape 1.0 to Grape 2.0, we are going to be going to this other hardware platform. We're working on the software. All of this is a process of continuous improvement. You can find it on the HamSci website if you want to join our project. We have weekly telecons, and you'll see all of the contributions of different members of the team today. We're going to continue long-term data collection in our own stations. We're working on analyzing the data that we've been taking in thus far in context of different data sets. Steve's presentation I'm looking forward to about connecting the observations we've been making with the theory of what's actually going on. And then our next experiment that we're setting up will be a long-term, this thing we're calling the Grape circle of this one bearing, and that will let us make 2D ray traces along that bearing and compare the data that we're receiving from the stations to that. And then finally, for short-term pilot experiments, I'm looking forward to creating citizen science projects that are more dynamic and interesting for people to participate in. And we'll be talking tomorrow about how to connect up science campaigns with amateur radio contests. And with that, a man who needs no introduction, I'm going to hand things over to John Gibbons, N8OBJ, and he'll tell us a bit about the hardware platform.
Thank you. Kristina, your timing was impeccable.
Thank you. I've got a stopwatch.
So we actually have time for a question or two. So Diego, are there any questions in the chat? Or Gareth?
I don't see any questions in the chat unless I missed one.
All right, well, why don't we go ahead then to John, and then if there's any extra time at the end of his talk, then we will take more questions then.